I'm Paul Selkirk. The title is After the Fire. We'll get to why that's cute in a little bit. And I'm from ISC. So for those of you who don't know, ISC is Internet Systems Consortium. We're a 501c3 nonprofit public benefit company. Our most visible activity is software. We provide open source internet infrastructure software. We're the people behind Bind and DHCP, and now this new product after. Basically, if it's got to do with IP addresses, we're probably in it. We also run one of the DNS root servers. We have a secondary name service for public benefit and enterprise customers. We do web hosting and mirroring for a select group of public benefit companies. But our big public things are DNS and DHCP. So that's who we are. Who am I? Why am I here? I'm the technical lead for ISC After. This is a new product. This is not intended as a product pitch so much as kind of laying out the problem space, the solution space, and what we're doing to try to be in that solution space. We're here to talk about the heat death of the internet. Now it's just the heat death of IPv4. And what we're going to do when we run out of address space, and the solution that we're in right now is called Dual Stack Lite, and is implemented in this brand new product. So, and the universal deployment of IPv6. So at the ITF, there are these Scotch bobs, and every toast ends with, to this or that person, and the universal deployment of IPv6. And someday we'll get there sooner than flying cars, sooner than gallium arsenide. That's it's going to take a little bit of doing. So to set the stage, we are running out of IPv4 addresses. We have been for a while. This has been a crisis for about 15 years. And unfortunately, we've learned to live with it, and the problem has not gone away. So the unallocated address space is down to about 10% of available, and with a burn rate of I think it's about 13/8 blocks per year. So we're going to run out. We'll get to that soon. So to be very clear, what we're talking about here, address space goes through a certain number of steps before it's actually provisioned on your laptop. There's the IANA unallocated pool. They have the address space that no one else has. They meter it out in units of /8 blocks. On an as-needed basis to the regional internet registries, who then parcel out smaller bits of that to the local internet registries and some of the bigger ISPs. They, in turn, parcel out smaller bits of address space to the enterprises and the smaller ISPs. And so, at every stage, there is a certain pool of unused address space, but what we're looking at is the big one at the front end. This is another important point, that once addresses are allocated, they almost never go away. There's no formal mechanism to reclaim unused address space. That happens at an ad hoc way at the enterprise level mostly, and at the ISP level. But nothing ever goes back into almost nothing ever goes back into the IANA free pool. And toasters use address space too. The story of the SNMP toaster. Okay, This was something that my former company, Epilogue Technology Corporation, did for a demo once to show off what SMP can do, and they had an SMP controlled toaster, so you could set toast down, toast up, light, dark, and query it. But that means that your toaster needed an IPv4 address in order to run this. So in the early days, when IPv4 was being designed, they were like, of course 32 bits is enough. What are you going to do? Put IP on every doorknob? And well, now we've done that. And so here we are. This is the XKCD map of the internet from circa 2006. I love this. It was kind of reassuring at the time that no, we're not actually running out of address space. But things have changed since 2006, and so all these address blocks are now allocated. Let's see if I have a pointer. So actually, one of the last ones, just this month, was net 1. So your canonical example IP address 1.2.3.4, that's going to be a live IP address sometime real soon. Here's this green O is one little bright spot that was originally allocated to public data networks and was reclaimed just a couple years ago. But in general, the curve only goes one way. This big block here in the corner, that's 240 to 255, is actually should not be considered green fields, because that's officially reserved for future use. That's not part of the IANA free pool. Nobody owns that address space. To get it into the IANA free pool would take intergovernmental action, and in the end would really only buy us year and a half at the current burn rate. So yes, I stole this graph from Jeff Houston's IPv4 reports. He's a researcher in Australia. He has done a lot of research watching the trends in IPv4 and IPv6 deployment. And so this vertical line is where we are now. The line to watch is this red line. That's the IANA free pool, and that's here we are now, and we're going to hit rock bottom. This is one of the magic numbers is 0, and we're going to hit 0. He's estimating September 5th, 2011. So what happens then? That's death of the internet part 1. This light blue line here is the regional internet registry pool. Collectively, there are 5 different registries, but it's aggregated here, and it's a kind of a sawtooth pattern, because anytime their address space gets a little low, they add another /8 block to that. So it's been going up and down, but at this point, this gets refreshed, and then it slides down to the magic number of 0 sometime a little later. The green line is addresses that are that the regional internet registries have assigned to their customers, and that is going to hit the magic number of about 220 sometime shortly thereafter. These are, let's see, the purple line is addresses that have been assigned but are not advertised in BGP. So they're not actually in use, but they do belong to, ISPs and enterprise customers. So this is kind of flattened out, and that's going to drop off. BGP, Border Gateway Protocol. So at the same time, advertised addresses is going to reach the magic number of 220, and that's when it all ends, because then there are no more addresses for anyone, no more unallocated addresses for anyone to play with. Right, minus this block, net 10, and other smaller reserved spots. Oh, okay. So, September 5th, 2011 is not that long. So we have to do something soon. What do we do afterwards? After we run out of the unallocated address space, we can't just stop. The internet still needs to grow. We have a lot more customers coming online. My parents are on the internet now. My phone is on the internet now. My TV is not on the internet, but yours probably is. So we need more. We need to serve those customers in one way or another. There was, the crisis of the '90s was more one of, we were afraid the routing table was going to melt down, and the address allocation was kind of clunky. Class-based addressing didn't turn out to work so well. So we got CIDR, classless routing, and we got the regional internet registry system set up, and so the allocation is a lot fairer, and the routing table works, but we're running into the address space problem. NAT only gets us so far. You can throw a lot of machines behind a NAT, but that you run into a lot of limiting factors there. So. Right. So the question was about reclamation, about getting /8 blocks back, and there is not a formal mechanism to do that at this point. There's no mechanism for address trading or address reclamation. Actually, the way Jeff Houston put it was, at what point does the current allocation policy become irrelevant? At what point does it totally break down and we need a new policy? Yeah.
So just to keep in mind, even if you got a /8 back in the ARN region, which is North America, Canada, some of Latin America, it lasts 3 months. So,
I get
right.
I guess
It's a losing game.
well,
Yeah.
it's not so much a losing game. Not so much that it's a losing game, that it takes people a long time to respond. It's like I know in past jobs we've had to do IPv6 support because the government was going to switch. Well, that was years ago, and they haven't done it. So it seems to me, doing other things to prevent us running out seems worthwhile.
And in fact, that's a good segue. What was supposed to happen? We were supposed to go to IPv6, and we were supposed to get there by everything going dual stack, and 6 to 4 and other tunneling mechanisms. That's encapsulating IPv6 in IPv4, tunneling it out, to the other little islands of IPv6. And we put a lot of the other pieces in place. The DNS supports IPv6, DHCP supports IPv6, and so we thought that the end user, were going to drive this this move to universal IPv6. But what really happened? There was kind of a collective yawn, and people went back to doing what they were doing in the way that they were doing it. There's no IPv6 killer app to really drive this. And I'll say this as someone who spent a long time doing IPv6 implementations, that IPv6 really doesn't give us anything other than bigger address space. Yeah, sure, there's this cool auto configuration stuff. There's the dentist office scenario where they just kind of plug their machines in and they find each other. But even the dentist office now is using a home gateway or a Soho router that has DHCP in it, so it's already got auto configuration effectively. So it all comes back to the address space issue. And what this slide adds up to is there was nothing really compelling driving the market to IPv6, and nothing really compelling driving the market away from IPv4. So unfortunately, it really kind of came down to the game of chicken, where we have to where the internet has to melt down before we actually go there. So it's a sort of a chicken and egg problem too, because the carriers aren't rolling out IPv6 because there isn't demand for it. There's not demand for it because the services that I need to get to are on IPv4, and my v4 still works. So what's the big deal? So now here we are, and we know where we need to go. We need to go to IPv6, but we need to continue to support v4 devices, v4 applications, v4 web services, and it's not all going to happen at once. We need to. I mean, carriers are going to upgrade their equipment when they get around to it. It's going to be staggered. We don't have a flag day for this, and everything needs just to continue to work. I need my Amazon order to go through. I need to get to Google. So there's been a lot of activity at the IETF level, but largely to this point in the research area. So we're looking at solutions like double NAT, and 6-4 we mentioned. 6RD is IPv6 rapid deployment, which happened that was rolled out in France. It's basically an extension to 6-4, and they basically rolled out v6 tunneling in a matter of weeks to their customers. But most of the rest of this has remained in the lab. There are a number of IETF working groups working on this stuff, or on pieces of this stuff. But it still hasn't really gelled in the marketplace. So what does any solution that we have here needs to work in the carrier networks? It needs to work in the marketplace. It needs to it needs to scale up to large carrier size deployments. Yeah, they need to be able to stagger it, and it's got to work no worse than the current net. You still need to be able to run your peer-to-peer. You need to run your home servers, and it needs to not be worse performance than what we have now. So now we get to one particular proposal in the solution space. This is the one that we've been working on. It's called DS-lite. It's currently defined by an internet draft, which means it's very much in the experimental stage. But it's conceptually, the concepts are very simple and very solid, and it's just a matter of working through the standards process and working through some of the small details. It's basically a combination of two well understood technologies, tunneling and NAT. And in fact, the way it works is basically you take your home gateway and you put your NAT out in the net, and you put your neighbor's NAT and all your neighbor's NATs out in the net, and you aggregate them into one NAT. So it's an address sharing solution. So rather than, I'm jumping ahead just a little bit, rather than everyone having one address that they share between all of their home systems, we have one address that we share around the neighborhood, which has some interesting properties. So this proposal has been driven largely by the broadband carriers, Comcast in particular. So they're thinking in terms of the home users, the end users, who have a few devices and who would be good candidates for sharing. They want it to be transparent to end systems, so it just looks and acts the same as what the customer has now, and it conserves IPv4 addresses by sharing them between customers.
It seems to me that it's also nice from Comcast's perspective because now they can more readily identify the people whom they can try to charge business or server class fees to, because now those people don't have the ability to offer a server because they don't have an address that they can request. From the consumer's perspective, it probably cuts down on the risk of various kinds of attacks against their home router because that's not exposed except in their neighborhood.
Yeah, it's jumping ahead a little bit. As far as the identifying the home server customer, there are mechanisms to request a port forwarding, but that's not a guarantee, and we might end up with something like you're describing, where we're kind of separating the real home users from the home businesses. So the DS-lite protocol, like I said, it separates the home gateway from the NAT. The home gateway is now provisioned with IPv6 only, and so it has to create a tunnel to the NAT, and so the basic things that it has to do are figure out where to send the traffic, encapsulate the traffic, and it now doesn't have to worry about NAT because Big Brother is taking care of that. few terminology. We refer to this home gateway as the B4 element, basic bridging broadband elements. And the piece that lives in the carrier network is the after, before and after. This is why you shouldn't let engineers name things. Look at all that, the IETF working group names. It's, at least this sort of means something. Anyway, the after, or the address family transition router, is the tunnel endpoint for a number of B4 elements. How many is up to the carrier. It decapsulates the customer traffic and nats it out to the internet. It takes internet traffic and does the reverse NAT mapping and sends that back to the customers. And then there are management operations around that. Security, access control lists are important, although I don't think I actually hit that on a slide. But there's the administrative end. But the basic technical piece is that it's the tunnel endpoint and the NATs. And because I need pictures to actually visualize what's going on, this is the really stripped down version of the topology. So we have me at home with a mixed V4 and V6 network. And there's my home gateway that is provisioned with V6 only. So it's passing a mixture of native V6 traffic and tunneled IPv4 traffic. So the native V6 just goes straight out to the V6 internet. The tunneled V4 goes to the after and gets natted out to the V4 internet. And then one of the important things here is that, notice that, my neighbor and I are both running the same private address space. So, this has to be able to disambiguate me from him. This came out much darker than I expected, but oh well. Because I'm an implementer, I think in terms of, okay, so what does the NAT mapping table look like? And the NAT that you have today takes a 3-tuple of the source IPv4 address and the source port and the protocol, and that's writes a new header with the mapped public v4 address, and this is now going to be an active public address, and the mapped port. So the only thing that happens differently in after is we now have the source IPv6 address uniquely identifies the customer, me versus my neighbor, adds that to the tuple, and so this this address is now a v4 address within my network as opposed to his network. But other than that, the mapping is the same. Source address, source port, and protocol goes to gets rewritten as a mapped address and a mapped port. So that's how the protocol works, and now we get down to the implementation. Where am I going, and what am I doing in this handbasket? We were contracted to do the initial development by Comcast, since they're also driving the protocol. The IETF model is rough consensus and running code, and we're providing the running code part of that. So this is they want to prove that this concept is solid, and is so solid that anyone can write it. They can have a third party come in and write it. one thing I need to emphasize is that Comcast's name comes up again and again in this talk, but they have not committed to deploying a dual stack light. They have not committed to deploying our implementation of it. They just want to make sure that it's at least fully explored and implementable. That's the level of their commitment to this. They may or may not end up deploying this. They may have a different solution in the end, or they may just go straight to dual stack and give everyone V6 addresses. This was initially funded by Comcast because they're a large carrier, and the carriers are feeling the pinch first. They are most in danger of. They're the first ones who are going to lose in the race to the bottom on unallocated address space. And since the problem is increasing number of customers, they're moving the solution to where the problem is, and saying, okay, our customers are now going to share addresses, and so they're also very interested in how does this scale, how can we incrementally deploy it. So having running code also lets them play with the operational aspects in addition to the protocol aspects. As far as IC is concerned, we're here to write open source implementations of internet infrastructure protocols that solve important problems like DNS, like DHCP, now DS-lite. This is what we live to do. So the actual implementation of the B4 elements, that's the home gateway. This lives on, this is the customer premises equipment, and to put it in carrier terms. It needs to, live in a resource-constrained environment like a home gateway, and in fact, very like a home gateway. In fact, it has been implemented, on a home gateway. It only needs to do, a few things to actually make it a B4 element. It can do other things, but the things that it really needs to do are to set up the tunnel and stuff traffic into the tunnel. So the implementation, we prototyped the B4 element on OpenWRT, which is a Linux distribution for home gateways. It was originally designed specifically for the Linksys WRT series, and in fact that's what we used. WRT 54GL was our first B4 element, and it works very well in that environment. It's provisioned with a V6 address only on the WAN side. It discovers the tunnel endpoint via DHCP. There's an internet draft that defines that as well. In fact, I think David, who wrote it, is in Mountain View. And there may be other tunnel discovery mechanisms written for this if the whole DS-lite thing really takes off, but that's the one we have now. That's the one we know works. So encapsulation is the easy part. Yeah, basically, we threw together the B4 element, and then we have not had to touch it, in the last year. It's basically dead simple what it does. The after element is where we've spent all of our time. This, needs to do the the basic tunneling and NAT operations there. It also needs to do some port reservation and port management. It needs to do possibly some rate limiting on new connections, but it also needs to be able to reserve ports to forward to the user. There's other administrative stuff around configuration logging, resource management. I think that's on another slide. Again, we're not looking at expensive hardware to do this on. This could be implemented in hardware on a Cisco, but we implemented it on a Linux netbook. That's what we've been testing on. That's what we've been demoing on. It doesn't really get any simpler as far as commodity hardware goes. So this is kind of proof that this can be deployed anywhere in anybody's carrier network. The architecture is really kind of dead simple. It's actually single-threaded, so that it doesn't have to do context switches and locking and such. And it's implemented in user space to make it easier to experiment, change things without having to rebuild kernel modules or even reboot the system. We make a change, shut it down, start it up again, and it runs over I don't think I actually have it in here, but it runs over a tunnel a ton 0, ton 4. Runs over a tunnel interface. So, yeah, here's where we talk about port reservation. If you need port forwarding now, you log into your home gateway by some web-based management system, and you request this port gets forwarded to this machine. Here, Comcast envisions a web portal that does much the same thing. You log into Comcast and request this v6 address gets this v6 and v4 address pair gets this port tunneled to them. The thing is that just becomes a request rather than a guarantee. You and your neighbor might both want to be running mail servers, and only one of you is going to get port 25 on that address. So that becomes an area of some possible contention. There's also dynamic port reservation, where an application can request a port that it can advertise on peer-to-peer networks. So the standard way to do that now is UPnP, Universal Plug and Play. There's also a NAT-PMP is NAT Port Mapping Protocol, which is defined by a now expired internet draft, but is also widely deployed in Apple networks. So I'm not sure why they didn't advance that to the RFC stage, but both of those would be supported now, but they both assume a single broadcast domain where you're directly connected to, where the client is directly connected to the NAT box. And so there have already been projects to kind of extend that and put a proxy in place where, I could be running a multi-layered network at home and already want this on a v4 network. And it just dovetails really nicely with what we need, which is to be able to forward, a port request, through the tunnel to the NAT. So the port proxy project is something that someone else is doing. We've also implemented a NAT PMP proxy and agent. We've also got support for straight pass-through. If you happen to have a public v4 address but no v4 infrastructure, that can get tunneled straight through, and that's a possible solution to my neighbor and I both want to run mail servers. And Comcast might come back and say, okay, for a little extra, you can buy, a full IPv4 address rather than a fractional address. And at first, I thought this was, just kind of a wacky edge case, but I can see, business cases where this pass-through, might have to be, side by side with the regular NAT case.
Are there any implications with respect to VPN or IPsec of this approach?
Those VPN and IPsec mostly already work through NAT, so we don't envision that the NAT traversal is going to be really any different in this case. Like I said, one of the design goals was to make this as much like your current NAT experience as we can. What are we doing for time? Oh, there's a clock there. All right. Good, good. Okay. So like anything that's conceptually simple, it gets a little hairy once you get down into the implementation details. So to make this as much like current NAT experience as possible, we need a certain level of proxy and application level gateways. We need ping to be able to work through it. FTP has to work through it. Although early implementations of NAT already broke FTP. And so now most of the FTP clients are using passive mode, so they will work through most NATs, even NATs that don't notice that, okay, this is now going FTP control connection, I better set up the incoming data connection. But we expect that to just work, so we included that FTP data connection gateway. So another thing that's interesting about this case is that since this is an encapsulation, we're wrapping the v4 packet with a v6 header, which adds another 40 bytes to the Ethernet frame, or whatever your transport, whatever your layer 2 is. So if you're running full-size packets through, you're streaming lolcats videos or something, you're going to have some fragmentation issues. And fragmentation is something we really want to avoid because it really clogs the network. And in TCP, we have path MTU discovery, but it's not always reliable, and we'd like to avoid having to do the whole path MTU discovery dance, where we send back packet too big messages. So we have a hack in there. Let's not call it a hack, it's a tweak, to rewrite the MSS option on outgoing TCP SYN segments. Basically, the TCP negotiation that says, here's how big a frame I can handle, here's how much data I can handle. And since we're rewriting the header anyway, we just go ahead and say, we'll just ratchet that down by 40 bytes. And that has proven to work really well in lab and in test implementations. And finally, any implementation needs to run well and needs to be scalable. So we have tested this generally in fairly small networks, with the small numbers of clients, but we fully believe this will scale up to large numbers of clients running on larger hardware. The limiting factor turns out to be CPU speed, because we do a context switch on every packet. And so that load tracks pretty well to CPU speed. It's much more of a limiting factor than, say, the amount of memory or the speed of logging or anything. So if you need more performance, you're basically throwing faster hardware at the problem. Or you're moving the after element closer to the users and serving fewer users and just deploying more small boxes rather than one big box. Okay, so in the real world, outside of the protocol area, we still have the operational and administrative challenges of logging and support. There's actually something that's not on here, which is that we would like to limit the logging to just what we need to log, just the bare minimum, because it chews up resources for one thing, and it chews up the resources. Just kind of writing out the log. It eats up disk space with logs that no one's going to look at, and it potentially can fill the disk with logs of personally identifying information. So personally identifying information in this case being what machine behind the NAT is requesting this. There's nothing with your name on it unless your name is the name of the machine. So what we've done here is, rather than logging every NAT binding, we allocate a bucket of ports to each customer, and as the connections come in, the NAT bindings come out of that bucket of ports, and then we allocate another one. And furthermore, we randomize the bucket so that the port allocation is not predictable. It's a small measure of security, but that means that when we write out the log, it's just this IPv6 address got assigned these TCP ports. So lawful intercept, the FBI can come in and say, we need to know about a customer using this public IPv4 address and port at this time, and they can still get that information. It's a little less trivial. They can still get what they need to get, but no more than that. It's just enough to identify, it was this customer. No, it will not identify the machine within the house. That source IPv4 information is not logged at all. It's just, that something behind this v6 address has gotten this binding. So we're kind of feeling our way around, what the law requires as far as lawful intercept, but we think this strikes a good balance. And then there's the whole issue of how do we support Comcast? How does Comcast support their customers? Because every time you add a tunnel, or a layer of indirection, you're really kind of adding an extra layer of complication to the debugging aspect. And so we also don't know how this is going to play well with native IPv6, with 6RD. So we're basically looking to our customers to tell us what tools they need. I'm almost done. And the end state that we're really driving towards is native IPv6. IPv6 everywhere. Everything. Let's see, IPv6 on everything, everything on IPv6. 6RD is a little bit orthogonal, or even at cross purposes to this, but it may help in other deployments, or it may be deployed incrementally. Like this neighborhood gets v4 and v6 tunneling. This neighborhood gets v6 and v4 tunneling. So we expect that there are going to be a variety of solutions that actually get deployed. And the carriers, probably will eventually, decide that, okay, this is all very interesting, these coexistence technologies, but let's just do native IPv6. It's easier that way. So they may decide to, just bite the bullet and step back. At which point we declare victory and go home. Except that we don't, because v4 has a very long tail, and we're going to need some kind of coexistence strategies. Whether it's something like, so whether it's an address sharing scheme like this, or whether it is okay, we've gotten a lot of people off of v4, and so we can now allocate v4 to anyone who still wants it. So when I was rehearsing this, my test audience pointed out that, okay, I'm going to talk to Google, and you guys are in a sort of different network space. So this is a solution that's aimed at the home customer. It's not aimed at the large carrier networks. It's not aimed within the large carrier networks. It's not really aimed at guys like you. Your solutions to running out of address space, would be largely the same as the carrier's solutions within their networks. You might deploy a net 10 within the network just to route things around, or you might deploy v6 within your networks and kind of tunnel the v4 through it. But again, the long-term answer is still the same. It's still IPv6. And since there isn't a v6 killer app, you could kind of drive that and be the v6 killer app. So now we have come to the end, and you have a question.
So from an enterprise perspective, this does affect Google, as we have small offices that don't have and may not be able to get dedicated internet services with or tomorrow, and we may have internal v4 only applications. Right? Additionally, for the customers we have increased latency concerns, we have increased MTU concerns, we have MSS concerns, we have DNS concerns, we have logging for lawful intercept or
Mhm.
for legal compliance concerns, all of a
Mhm.
sudden now we have to say, by the way, it was Paul at this IP address and this port. We were not necessarily logging port today, perhaps. So
Mhm.
there are content people and enterprises in general.
Mhm.
This does touch their space, but
Okay.
Something they should keep in mind.
Awesome. Any other questions? Questions from the remote sites?
Question on the performance of the CPE or your B4 element. Can it actually push something like 10 megabits per second or maybe 20 down without falling over?
Well, I mean, it depends on the hardware. I have, pushed my Linksys device to the limit that it will go to. But the limiting factor there is actually my cable link. So I guess that's another part of the question is that if we're looking at where this is actually going to be deployed, this is going to be deployed on cable and DSL, and it's not going to be really it's not going to be on the ZPS networks. So any home gateway that is sufficient for that now should not have a problem with the added load of encapsulation and decapsulation.
Right. So another question. So do you see DS-lite being used for stuff like fiber to the home? Like Verizon has their Fios, right? I mean, presumably they could push a gig of traffic. I mean, obviously, you're probably not going to have a Linksys for as a CPE device, right? Or could it? I mean.
Yeah, I'm not actually that familiar with fiber, so I don't know what the terminating device is at the home now. But
it does is convert a fiber signal into basically just a standard copper Cat5 handoff or something.
Has any benchmarking been done either by you or by vendors like network vendors, Comcast, or equipment vendors, Linksys, D-Link, Netgear? And I would even extend that to say, is there a way we can, deploy this ourselves and connect to an after device somewhere in the world and test to see what sort of things happen?
yeah, I mean this is all open source technology, and you can download it and test it out today. You can the B4 build instructions are specific to OpenWRT and Linksys devices, but you can adapt that to anything that can create that tunnel, and the after codes, like I said, runs on anything from a Linux netbook on up. So yeah, you can certainly play with it now. I have the world's shortest IPv6 tunnel in my house. Actually, it could be shorter. It could be a 1 foot cable, but it's a 3 foot cable. So I actually have this kind of horrible setup where, since I don't have native v6 in the home, I've got my devices behind the B4 getting tunneled, to the after device, and since I haven't put the after code in my home gateway, it's getting natted, and then it's getting natted again, going out to the internet. So it's the kind of the world's the worst of all worlds that I have now, but I don't notice a performance hit. Even with all of those all of that hokey pokey that it's doing. Oh. Other questions? We're a little over time. Crickets. All right. Well, thank you for coming.